That's it. Without further ado, we have some really exciting talks planned today, starting off with Enrico Tassi, who is a researcher at the INRIA Sophia Antonopoulos and a member of the CoQ development team. He did his PhD at the University of Bologna, where he worked on the design and implementation of Matita, math components team on odd order theorem. Sorry, I'm reading Catherine's notes here. So, Elpi is so today he's going to be talking about Elpi. Elpi is a high-level programming language designed to implement new commands and tactics for the Rocq theorem prover, which is what he's going to be talking about. Good. And that'll be followed by 2 talks, one by Joshua Cohen and one by Thibault.
Okay. Thanks for the introduction. So yes, the plan is to talk about this language LP2 that allows you to write new commands and tactics for Rocq. I will give you a soft introduction of the language. I will give a demo on how it is integrated in the system, and I will compare it with the alternatives. But before that, I want to start talking about something that makes me proud. I selected 4 projects that use LP, and I will advertise them, but also pinpoint which are the key features of LP that these projects rely on. The first one is Hierarchy Builder. It's a domain-specific language to describe a hierarchy of interfaces and organize a library around it. Just to help you read the snippet here, hbmxin is the name of the command that is implemented in LP, while the record declaration is an argument to the command, and the command is registering this piece of interface into its database. Then later one can assemble these pieces of interfaces into the nodes of the hierarchy that we call structures, as I do here. And then one is in business. He can, for example, postulate a monoid M, a point in the monoid, and try to develop his abstract theory of monoids. In this case, maybe not writing a property which is false, but that's not the point. The point is that a lot of boilerplate is generated automatically behind the scenes using the extensive LP APIs. The HB generates modules, and then it generates for each node in the hierarchy coercions between them. It instruments the unifier of CoQ to compare them properly. It sets implicit arguments, abbreviations, all the kind of boring things you don't want to think about. And given that it has a first-class representation of the hierarchy, it can implement nice commands like there is one called how-to. You ask in the system, I have this type, I want to make it an inhabitant of that interface, which are the pieces that are missing, for example. Or you can draw the interface by generating a dot file that then you can display as you like. And what I really like about this project is that, about HB, is that when we port the mathematical components library to it, it kind of unlocked the growth of the algebraic hierarchy. The red line in the graph down there is the number of interfaces up to 2022, and the number was stagnant. It was really hard to add more interfaces. And the green line is when we started to port it to Hierarchy Builder. Now, most of them are defined using this tool. And they are growing, especially the order theory part of the mathematical components library got way more complete after that because they could add so easily more interfaces and make their theory grow. Another project I want to mention is Rocq. That implements a form of gradualized univalent parametricity. It allows you to transfer, let's say, proofs, statements from one type to another one, and it works roughly like so. You define a relation between 2 types. In this case, the very simple example, natural numbers and binary natural numbers, and then you also put in relation the symbols, the constructors for the natural numbers, and this successor function for the binary ones, and then you are facing a goal on the binary numbers, but you want to go back to the world of unary numbers where you have more proof tools. Well, you just call the tool, and you are back into the realm of nuts, and then you can use a theorem about natural numbers. The key features of LP that it uses is that the translation is implemented with rules, and when the user registers this relation is just adding rules to an existing program. It is extending it. And moreover, when it does a pass over the term to transport to the other world, it collects constraints, another feature of Elpi. And then at the very end, it looks at the constraint and it checks which are the axioms that one needs in order for the parametricity translation, for the univalent parametricity translation to work. Most of the times you don't need univariance, for example. Okay, so even if the translation works beautifully everywhere, if you have univalence, you don't really need it all the times. And this is what Rocq does. Derive is a framework for synthesizing code automatically out of data types declaration. It is actually the first application written in CoqPL'25, and I presented it in this very workshop in Los Angeles quite some time ago. To help you read what happens here, derive is the name of the command. This is an argument, which is, well, just a record declaration. And these attributes are options for the command. I'm saying, please put all the derived notions inside a module and synthesize for me an equality test and and the laws of lenses. So here you can see that he created a module, he put the type in it, and he also synthesized an equality test. As you expect, it says, I can compare two boxes if you give me a way to compare the contents. He won't ask you a way to compare the tag because it's a natural number, so there's already an equality test for it. Lenses in the Coq community are sometimes called record update syntax. Lens comes from Haskell, I think. The idea is that you have a lens, in this case underscore tag, to focus updates on a field of the record. And it also synthesized for me this little theorem, among others, that says that if I have a box R and I want to perform two updates with X and Y, well, if I first write Y there and then X, then what comes out of it is X, so the second one wins. And there are a few derivations written there and some more in the wild, proprietary code. Apparently a company likes to extend it and run it, but not all code is public. And the last project I want to mention is Algebra Tactics. You're probably familiar with the ring tactic for Coq, and you probably like it. I like it too, but in the mathematical component library for a long time, it just didn't work. And the reason is that ring is a reflexive tactic. So there is a meta program that looks at the syntax of your goal, recognizes operations of a ring, the types of ring, and then it translates them into a data type. And then there is a program, proof correct, that runs, that really implements the ring simplification on it. Unfortunately, in MathComp, recognizing ring operation is not so obvious because there is a hierarchy of structures. So maybe you have a field, but the operation is from a ring, so there is a projection. So the work of the reification phase needs to be a bit more clever. And in particular, this tactic makes use of the possibility Elpi gives you to call the unification of Coq in a very surgical way. And what makes me happy is that all in all, the performance of the reification procedure that Katsvik obtained is pretty good. So they have an example in their repository with a 500 lines polynomial. And the new ring tactic, let's say, solves it in dozen of seconds, something like that. And the reification phase is not the dominating factor. Okay? So even if it's smarter, if it does unification here and there, it's still acceptable. Okay? I wouldn't say it's blazing fast. Of course, it's lower than the standard one because it does more work, but it's still acceptable. Okay. Now what does it look like? So from a programming language perspective, Elpi is a constraint logic programming language, and it is a dialect of both Lambda Prolog and CHR. CHR means constraint handling rules. Maybe you never heard of CHR, it's not very important. You surely heard of Prolog, and when people hear Prolog, they say backtracking, this is the interesting part of the language. While no, I don't care, you almost never need it. What really matters to me is that the code of Elpi or Lambda Prolog is organized into rules. And it is really the life motive of my talk. I will try to point out where it really plays an important role. These rules are applied following a pattern, and more importantly, these rules can be added both statically to a program or dynamically at runtime. Rules look like this. There is a head, and it really means if the goal looks like this, well, solve it by generating these two smaller goals. The languages are from the 90s, so their syntax looks a bit vintage to me today, but I couldn't find a better one, so I kept it. And there is a convention that variables, parameters of rules are capital letters, and the lambda abstraction is written this way. So this is lambda x point t. Okay. So the hello world example of lambda prolog and also Elpi, even if I will try to push it a bit further, is a type checker for simply type lambda calculus. This is the syntax you use to declare an algebraic data type. The type of terms has two constructors, up and lam. Up packs together two terms, y in higher order abstract syntax style. The lam node packs a function of Elpi to represent the binding of a variable in an expression. Okay, and for the types, I just have the arrow constructor. Okay, so this is how you would write in this syntax the first function, lambda x, lambda y x. Okay, now the type checker is a predicate that relates a term to a type. There is this input-output annotations there. I will come back to them in a moment. For now, ignore it. And then the type checker reads pretty much as on paper. So if we have to check the application of a head to an argument, well, the head better have as type an arrow type from S to T, and the argument better have type S. What is more interesting is the rule for lambda abstraction. Remember that here f is a function, okay, of Elpi. So we assign to a lambda an arrow type from S to T. Now we have to synthesize T looking at the body of f. So what do? We postulate a fresh symbol, let's say a constant C. We add to our program a rule that this C has type S, okay? And then we do the recursive call on the body of the function to recover the type T. And by passing the fresh constant to the function, we are replacing the bound variable by this constant, okay? So I will run the program on this little example. So, of course, the second rule is the one that applies. So type first is going to be arrow. Okay, there will be a fresh symbol C that replaces the bound variable x. So this is the bound variable x. It is replaced by C. This is the type we synthesized so far. We are recursing over the target of this type. And we have added here to our program an extra rule that says that C has type S0 in this case. And we repeat the thing. Now our original type has grown. It is almost correct. It says there just is not correlating, it's not relating the input, the first input to the target type yet, but there is still a goal to be solved. We are asking which is the type of C, and this type should be T1, but here in my program C has type S0, so T1 and the S0 must be the same. So in the end, the type that is computed for us is alpha or beta or alpha. That is what we expected to find. So this was all known in the 90s. This is pretty standard lambda prolog. But if I want to use this language in the outer layers of Rocq, I need to be able to manipulate open terms, terms that are not complete, that contain holes. Okay, evars in the Rocq slang. Okay, so this is a kind of term I want to feed to my program. Okay, and here it fails. Actually, if you know a little prolog, you wonder why it fails instead of diverging. Okay. Because prolog would consume some input, then find a term which is not rigid and start to generate all possible terms. Well, not really all of them, but while here it fails immediately because of this annotation here. Input really means use these patterns to match the goal against these patterns instead of unify the goal against these patterns. So it's really, you really look at them as OCaml pattern matching, really, no, rather than unification if they are flagged as input. So here the program stops, but I don't want it to stop. So here it comes constraints. I add a rule that says if my input happens to be a variable, a unification variable that I call E, Well, I generate a constraint of the same shape. So in a way, I suspend the current goal. And I schedule its resumption as soon as E materializes, okay, as soon as the input materializes. So now this succeeds and gives me two constraints, that the head has type ROST and the argument has type S. Now what happens if later in the program someone assigns H, for example, to the identity function, okay? We expect S and T to become the same because the identity function is type alpha rho alpha, of course, and this to propagate there. And this is exactly what happens if we chain the first goal with another one, okay? And what makes me think that all of this makes sense is that I obtain the same result as if I had plugged the identity function right in, okay? So I'm just changing the order in which the computation really takes place, but it doesn't change the result. So I'm happier. But not completely. For example, if I try to type check self-application, this type system should reject it, okay? But I end up in this situation, which is not something I want. And this is where constraint handling rules come into play. I can add this rule that says if the constraint store contains two typing constraints on the same X for T1 and T2, that this bar means remove the second one and put back an equation. So try to unify them. And in this case, they don't unify, so the program fails. Okay? And that's pretty much all about the language. Now, questions, maybe? Now, what makes it useful? Sure.
Oh, yeah, now it's on. If you could clarify the status of these UVARs, so how, I guess maybe you talk about it in the next slide, how they're integrated into Coq, or is it just a separate constant UVAR, or?
I will say a bit more about that, but
because it seems like similar to
keyword,
app and lam.
It's just a keyword. It's a special case.
Okay, it's a special keyword in
some Prolog implementation. You would have a specific language to describe delays. Say delay when. I don't have this language, but I have a bit of a hackish syntax to do the same. It gives me more freedom of how to compute what to suspend on, because I have my own language to describe it rather than a built-in one. That's it. So now, when it is integrated in Coq, of course, you have a description of the terms of Coq in higher order abstract syntax. I won't show it to you because you usually don't need to know all the details for little demos, because you have a system of quotation and anti-quotations. For example, this is an API to print a message. And these double curly braces jump from the world of Elpi to the world of Coq. So inside here, you have a term written using the Coq syntax parsed with the Coq parser. Okay? And this Elpi colon curly brace goes back to the world of the syntax tree of Elpi, where I build an application. And maybe this term construction should talk about, because we will see it. Global is the coercion from references to global notions to terms. Okay? It's global constants that are available in the environment of Coq. There is a notion of databases of rules that can be extended programmatically. This will be used in the demo. And there is an extensive API, for example, and it's very tiny to read, but there is a way to ask the Coq environment all he knows about an inductive data type, like the list of constructors, their types, how many parameters, if they are uniform, is it inductive, co-inductive, all these kind of things. And that's it. So maybe the main point of this slide is to show you that the entry point to all the documentation is the GitHub page. And here there's a menu. As you can see, there is a documentation section with tutorials and proof of concept, so that you don't necessarily need to start from a blank page. You have something that looks like what you want to do, and then you play with it and you make it grow to your needs. So now I would like to make a little demo. Great. So I will implement a little proof transfer tool, very basic, very stupid, but it will allow me to show you many features of the language. So imagine that I have a predicate in prop that says is even, as you can expect, and an implementation of it as a Boolean test, okay? And imagine that someone proved that they are strictly related. So reflect really means if and only if. So if this Boolean test evaluates to true if and only if the number is even, okay? And I also have something for connectives. These two Boolean tests and their Boolean conjunction evaluates to true if and only if P and Q holds, assuming that big P and small p are in if and only if relation, and the same for Q, okay? The last piece of infrastructure I need is a limT that says, well, it's projecting one of the directions of the if and only if the proposition and the Boolean are related and the Boolean is true, then the proposition holds, okay? And now I have this goal in prop, and I want to automate the writing of this ugly line that allows me to switch to the world of Booleans, where I can compute and use reflection in a way to solve my goal. This ugly proof term I wrote by hand as a fixed part, which is a limT. We are going backward to the Booleans. This whole here is the subproof that is generated, and what really the work of the tactic will be is to synthesize this term looking at the type. So how do I do that? Let me maybe put it here. To bool. Okay, so the entry point for tactics is called solve. It takes a goal. A goal has many arguments, but what really matters to us is the type we have to inhabit. Okay, and the idea of solve is that it takes a goal and generates a list of sub-goals. This is how the entry point is supposed to work. So we want to, at the end of the day, we want to refine, it's called a limT of a certain proof that I will synthesize, and that's it. So this is the scaffoldings, and now I will write some code to synthesize this P out of TI, okay? Let me call it this TB. So it takes a term to a term, and my invariant is that TB R is that R is going to have type in Coq reflect P of something, okay? So if I find is even of some n, well, oops, the term I want to generate is even P of the same number. This is the first rule I put in my program. While if something for conjunction, a bit of, if it looks like P and Q, well, I use the NP, and then I need to pass to it a proof for P and a proof for Q, okay? Let's call it this, PP, PQ, and then I do the recursive calls. P will give me the proof of P, and the recursive call to Q will give me the proof for Q. That's pretty much it. So now if I remove this, and I didn't do mistakes, the new tactic does the same thing as before, okay? So maybe it's okay, but maybe not. What I don't like about what I wrote right now is that if I'm adding a new lemma, like for Boolean disjunction, whatever, I have to come back here and fix my code, okay? But I want my code to continue, evolve, and work as the library grows, okay? Now everything is on my screen, so maybe it doesn't look like a real problem, but so how do we do that? First, we declare one of these things that I call databases, to bool.db, and this database will contain rules for one predicate, this one. Sure, just let me finish the sentence. Okay.
how is the two-bool tactic wired up with, like, you have an Elpi tactic two-bool, and then there's a next command, which that's a completely separate command, right? But somehow they are connected to make the two-bool tactic
All right, sorry.
wired up with the solve thing?
Commands and tactics are made of many pieces of code that you accumulate together. So this means, let's begin the definition of the two-bool tactic. This will accumulate on top of it some fixed code, okay? And then you can repeat this many times. There is no end, really, okay? They are open-ended, the program. So I didn't put a delimiter to say this is the end of the definition, because the definition is meant to grow anyway. I don't know if it makes sense.
Okay, yeah, makes sense, thanks.
Shredder, sorry.
Just a quick follow-up to that question. So you could say two-bool, accumulate rules, then you could have another tactic, accumulate rules, and then could you switch back to two-bool and add?
Yeah, sure. You can do that, but the more civilized way to do that is via databases that I will just demo. Maybe Brigitte has a question. I don't know if it was the same. Okay. So the idea is that I have this entity, a database that can gather rules for the TB predicate and can be extended programmatically. Now my tactic won't have this code anymore. Okay, I just commented because I need it. My tactic will accumulate the DB. Okay. And of course now it fails because the database is empty. There are no rules. Okay. Now what I want to write is a program that takes stuff like this. I want to implement a command that does this: register NP and register, how was it called? Even P. Okay, this program will take these Coq terms, compute their type, use the type to synthesize rules and add the rules to the database. Okay. It will essentially synthesize the syntax that I wrote here and put them in the database. Oh, sorry. Now we are in another world, so another way to make comments. The main difference is that when you programmatically describe a rule, you need to make all quantification explicit. So this rule really should look like this for all n, while this one should really look like rule PQ, PP, PQ, and stuff like that. Okay. But other than that, are really the same rules. So let's do this command. Register. Okay, so this time it will be a bit more tough, but okay, we will do it. So the entry point for comments called main. It will takes a list of arguments, in this case a string. Then there is an API to locate the string and get a global reference, like a pointer to the environment of Rocq. Then all global references have a type. That's pretty much what Rocq is about. And now we will compile this type and the global reference in order to obtain a new rule. And then I will add my rule to the two-bool database, and the rule is going to be like this, okay? A bit of mouthful. There are many options I don't want to even talk about, but the idea is that I synthesize some code and I add it to the database, okay? Now, my function to synthesize this code will be fueled by the type, okay? The proof and the invariant is that the second argument, global, the second argument is a term of type, the first argument, okay? This will be the invariant during the recursion, and I will need an accumulator to remember the recursive calls. So let me write it here. Fix a term, another term with the invariant I just said. a list of recursive call, list of propositions, a list of predicates, let's say, and it will generate the proposition. So when the type I'm looking at is reflect of some S, and I have a proof of this reflect, and I have something to do, well, the rule I want to synthesize will be tuple of the proposition that is in the first reflect argument, and its proof will be R, and proviso that I do everything that was left to be done. Now, the type of the theorem could contain an arrow with a reflect on the left, an hypothesis. So if it looks like reflect S arrow tie, okay, I have an R, I have a to-do. This time I will have to synthesize the theorem as an argument, so I need to quantify it here. So the rule I'm going to generate will start with something like this, okay? I will make it explicit. Now, in higher order APSA syntax tradition, whenever you want to move under a binder, you write a pi. Okay, so let's assume I have a variable for that. I have to do my recursive call on tie. Okay. Now if this has type arrow, the recursive call is on tie, so the conclusion of the arrow. So I need to apply this R to the term that plays the role of the abstraction, so H. I have to remember it will be a recursive call, okay? So I have to remember, this is how you write cons. I'll have to remember to transform S into a Boolean, and the proof is going to be H, okay? And then I do the recursive call on, I will synthesize the body of the rule. And the last case is when the type of the theorem is for all x tie, and in this case the type depends on x. This is the syntax how you say that. There is an R, there is a to-do, and even this time I have to do something like this. So I do as I did before. In order to do my recursion this time, tie depends on x, so I need to pass something to x, to it as well. My proof term has to be applied to x as well. I will keep the same to-do list because it's not a recursive call. So, for example, here I had for all p, q, etc. These are not recursive calls, while these are. So this is why I'm not touching my to-do list. And this should be it. Now, I lied to Ralph a little more. No, it's not. I didn't lie. It's just that I need a command to say that register is available without writing Elpi register. Okay, so, and this usually goes at the end of the definition of a command. But the command is still open-ended because it accumulates the database. Okay, so a bit like the tag. So it's not really ending the definition; it's just making it available. And now, if you go back to our to our proof, we have the same tactic as before that works, but we populated the database of rules programmatically. Okay. Now, this is a bit of a mouthful. If you're used to higher order APSA syntax, it's kind of trivial. But if you're not, I understand you. You may look at me with eyes, okay? But believe me, you get easily acquainted to it.
The two underscores in clause, I was sort of expecting that you'd have to specify what those are on line 53. When you call accumulate on line 53.
Yes. You mean this underscore?
No. 53.
53, sorry. Well, this is in all my APIs, arguments with a default value can be passed as an underscore. So this is where the rule should be put. This the name of the rule. This is an unnamed rule. And this is a grafting point because you can say, I want to graph this rule before that or after that. And by default, it goes to the end of the database. So it's just a syntax for default arguments. Sure.
So this is really cool. I have two questions. So one is, so you might be in a subgoal that has some variables introduced because you're proving something for all. So currently in your lemma, it's like ground, essentially, right? So how do you make sure that, for example, the natural number then, because that might live in some kind of other context where you already have like some bound variable, because you're proving something about for all natural numbers, for example, right? How do you make sure that you respect that binding?
Respect the binding,
or like basically you have not only, I mean, your numbers are not going to be closed. So you wrote, I think, in one of your rules that you need to write the pi explicitly, and the pi was :nat, and it's not.
I'm not so sure I will answer your question, but
okay.
I will add something. So, for example, there is I try very hard to give you the illusion that that the programming language handles for you the context, as in the proof context, and EVAR maps, so the type and value assignment to unification variables. So here I moved inside a term, okay, using an eigenvariable, okay, a variable that is bound by the context of Elpi, of lambda prolog, without losing some information. For example, this could be nat, okay? And there is a convention that whenever you want to do this term traversal properly, you add to the context of the programming language something like this. Well, this I really don't care. Yes. So in this way, the variable really corresponds to a Coq one, and deep inside the term, I know its type, and that's it.
Right. Okay. I have another question.
Okay.
So, I mean, when you do this compile, if I understand correctly, you're compiling lemmas also, right? Is that correct?
So this is the name of the lemma. Oh, sorry. Oops. This is the lemma, the proof of the lemma, and this is its type.
Yeah. So let's say you had early on in the example, you had this arithmetic solver, which where we might prove some properties about plus, like commutativity of plus or associativity of plus. Now, these are then rules in your logic program that can always be applied.
Right.
And so do you bound the search of the logic program? Because, I mean, when you call it as a tactic, right, it might go on forever.
Yeah, sure. No, there's no magic. So
okay. If it goes forever, it just goes forever.
You can say LP bound steps 27,000 if you want, or you can be careful when you compile or write down by hand your rules so that it won't diverge. There is no magic. Okay. Maybe in the conclusion I will hint at something, but for now nothing is there. And there is another question that maybe I should continue. I don't hear you. No, it doesn't.
Okay. Now it works. How are overlapping rules handled? Because, like, technically, it seems like the for all and the arrow before could overlap, like the last two of you compiled.
Well, this is a non-dependent product that it has on the left anyway a reflect.
Yeah, but like if you like also the second one would match, right? Like if you have a reflect, you could also see.
Yeah, sure. Okay, to answer you, this is how I would have written, but I didn't want to give. This means commit to this choice. Both match, you're right, but I want the first one to be selected, and if it's the case, when there is a reflect, I want the first one to be selected, but not the second. And you put a bang in.
Okay, but like the order also.
The order matters. It's really operational. It's not.
Okay.
Thank you. So I really have to go back to the, yeah. Well, okay, maybe well, I had questions. So that's good. In the abstract, in the short abstract, I compare it also to OCaml, LTAC1, and MTAC a little. Here I just picked the the two friends that are currently developed and actively developed. So all of them, all the languages have representation of Coq terms. The one of meta-Coq and LTAC2 is complete. They have all the details, even the details I don't like to see. For example, Rocq is coded in locally nameless, so you have variables by name and variables by the Bruijn indices, and you see this detail in LTAC2 and meta-Coq. In Elpi, you have higher order abstract syntax, so it's a bit more high level, but it's not complete because I didn't get to the implementation of mutual fixed point and mutual inductive types. This is a limitation for now. Support for bound variable is very easy. Once you get acquainted to higher order abstract syntax, it's very easy to manipulate bound variables. I mean, you have nothing to do. While LTAC2 and meta-Coq don't give you any support at the language level for that, of course you have quotations, so sometimes you can avoid writing the Bruijn indices, and in the case of LTAC2, quotations can be nested a bit like in Elpi, so you can get away with it more often, but still the complexity is there. All evers, they're fully transparent in Elpi. We never wrote an ever, we never threaded a substitution in the programs we wrote, so it's very high level. While in meta-Coq you have the node ever in the syntax tree, but no support for it yet. In LTAC2 is halfway because it's like ML, but it's implemented on top of the proof monad of the tactic monad of the proof engine of Rocq. So this tactic monad has a state, and the state is the ever substitution, so you don't see that. You don't have to thread around a state, but still you have to use APIs to manipulate evers because they are not a primitive notion of the programming language. About the proof API, LTAC2 is clearly the most advanced one. From the very beginning, that was the objective, I think. meta-Coq doesn't have much there. You can fire type class resolution, and you can start a proof, but you cannot really do much. In Elpi is not too bad, but I'm not too happy either. There is a bridge to call LTAC1, which is a bit weak in my opinion. It's very fine if you call a tactic that solves the goals. If you call a tactic that gives you back goals, you can do that, but it's a bit annoying to deal with it. I should really improve on that. Script in the vernacular, it's really where Elpi has an advantage over the others. The only thing that is missing are the notations, the one with a long string, that are so ugly that I didn't get my hands on them. And I cannot start a proof. I cannot write a command that starts a proof obligation. Okay? In meta-Coq is minimalistic. You can read and write from the logical environment, but that's pretty much it. You can start a proof otherwise. And where meta-Coq stands out is that you have a tool with a reasoning logic to reason about your program. That is Rocq itself. That's so they didn't do artwork for that to work. It was already there. It was a smart choice. You have nothing like that for Elpi or LTAC2. I just wanted to mention Abella, which has a semantics for lambda prolog, and you can reason about lambda prolog. Elpi has much more than lambda prolog. It has these constraints, and you need a few non-logical features, so it's not usable out of the box. If someone wants to do it, not me, but if someone wants to do it, that's a start. And to conclude, so I wanted to say a few words about the role I like the word extension language, and I like to think at Elpi as an extension language because it makes you think that from the very beginning, from the inception of the language, it is going to be used to extend a larger application. So you work from the very beginning to have a good FFI to exchange data with the host application, and this results in many APIs, and this is the strength of the language today. And you're allowed to use the language only when it is a good fit. Implementing the entire Rocq in Elpi would be completely insane. But it proved to be, using Elpi for little extensions proved to be pretty handy. And the other point is that maybe we should look more into rule-based programming language. We use the rules to handle the context, the local context of our computation. The type checker I showed you didn't have a gamma. All the type checkers have a gamma, but this one didn't have because it's the programming language that gives you one. And we also extended the program with global rules that matched how the environment of an interactive prover grows. I mean, as the environment grows, you prove new definitions, new theorems, and you want to add rules so that your programs continue to work and take advantage of the new contents of the library and vice versa. And also the fact that the code unit is so simple, it makes it simpler to synthesize one. If we had to modify an entire ML program, we could do that. We would have to traverse a much more complex syntax artifact, and we could do it. While here it was trivial to just synthesize a little rule and add it. And for the future, so what I'm working on with the students is a type class solver written in this language. A bit like the compiler I wrote, but more sophisticated. And it goes hand in hand with something that we are going to do at the programming language level, a static analysis for determinacy, which would mean in Haskell slang, it would mean overlapping instances. We would like to detect them statically so that if you load two Coq libraries, you know if something is going wrong, if immediately two notions become a notion becomes ambiguous. And well, users want the features that I highlighted I don't have, so eventually I will add them. And the last thing we started working on, but we didn't finish, and this should answer a little the question of Brigitte before, is that we studied memorization techniques for logic programs, and that could make the language a bit more declarative. We hope to gain speed in type class search, but actually we don't have good examples because all the examples we could find are not very demanding after all. And also in our experiments, it takes more time to type check the proof you find, the instance you find, than to find it in Elpi. So we left this memorization track a bit on the side for now. And that's all I wanted to say. Thank you for inviting me, and thank you for contributing code.
Yeah, thank you. I think there is time for like 1 or 2 questions while the next speaker can already set up.
So for having done my fair share of logic programming,
So what we do right now is that we hook into the mechanism of Coq. So you still declare an instance, and we also compile it for our solver so that you can really compare the two solvers. And the preliminary experiment, I mean, we managed to compile TLC, STD++, a bit of Iris. Okay, so we didn't compile everything. And then what we see is that we are competitive in performance. Typically, we are slightly faster, but the dominating factor is type checking the instance, as I was saying. So even if we get 10 times faster, it changes nothing. So we will have to dig deeper, I think.
And also, quick question: can you add commands that add new instances?
Absolutely.
Yeah.
You can either write the instance rule by hand or write a command that synthesizes it as I did in the demo. Yeah. Sure.
Okay.
So many questions. So what about if you have some kind of dependently typed data type you've defined? So since you're restricted to lambda prolog, right? So I mean, for example, you have here, you had early on this example of TM, right? You specified this the lambda calculus essentially, but it is a reflection of what somebody maybe had written in Coq, right? So in Coq, maybe I would have written something that is already intrinsically typed. And then I want to reflect the rules, right, still into Elpi in order to work with it. Is there any way you're thinking about extensions to that? Because there's sort of this mismatch, right, of power.
Yes, but I think, okay, I didn't show it, but the syntax I wrote and the syntax I use for Coq, the one for Rocq is a bit more deep embedded than that. So the type system of Lambda Prolog is too simplistic to match the one of Coq, so it's kind of loosely typed, the syntax tree you would get. So the extra constraints you get are in the type system of Coq. You can check them calling the type checker of Coq or do something on your own, but the language won't help you there.
Okay, all right,
thanks. Okay, thank you. Let's thank Enrico again.
Thank you.